Good morning, students. Welcome to our online classes once again. As you know that in previous classes we have covered moving coil instruments, moving iron instruments, and also dynamometer type instrument. These three instruments generally used in our electrical laboratory while performing our experiments. As a electrical students, we should know the difference between moving coil and moving iron instruments. At the same time, how to use the wattmeter with more settings like current setting and voltage ranges. In previous classes, we have seen each and every part of a instruments. What are the different parts in a moving coil instruments, like how deflecting torque is produced, how controlling torque is produced, and also how damping torque is produced in moving coil instrument and moving iron instruments, and also in wattmeters. These instruments can be used as a voltmeter, ammeter, whereas dynamometer type instrument can be used voltmeter, ammeter in addition to wattmeter. Now we know that these meters performed perfectly gives accurate reading, but it has some errors during its working time. What are the common errors in instruments? Let us concentrate that one. Now, what are the objects today? On completion of this topic, you would be able to know the common errors in moving coil instrument, the remedial measures for the errors in moving coil instruments, the common errors in moving iron instruments, and remedials in moving iron instruments. Similarly, the common errors in dynamometer type wattmeter instrument and the remedial measures for errors in dynamometer type wattmeter instruments. What are the common errors? Here, the common errors, if you are observed in any type of electrical instruments. Electrical instruments means the physical quantity to be measured in terms of electrical energy. Whether it may be temperature, either may be voltage and current or anything I want to measure, that is converted into electrical signal. That is indicated on a calibrated scale, the intensity of that values. Now, main common errors in our electrical instruments are generally the temperature errors, frictional errors, mechanical unbalance errors, observational errors, and aging errors are very common in our electrical instruments. In case of instruments, those are used in AC as well as DC. Further, one extra error is frequency errors. As we know that the coil in moving coil and also the coil in moving iron instrument, electromagnetic coil, and in dynamometer type also we have the coils, fixed coils and moving coils. That is nothing but armature. If you know that armature is producing deflecting torque. To produce the deflecting torque, it requires some magnetic flux is required. To produce the magnetic flux, we require some inductance coil is required. The coil which has its own resistance inside. Once the variable which is given to the input as a voltage or current which is passing through this coil, the coil contains a minimum resistance through which the current flows. I square RT by J heat will develops. This heat will changes the resistance of metals. We know that all metals are positive temperature coefficient metals. If temperature increases, the resistance also increases. If resistance increases, the current value decreases. If current value decreases, the flux decreases. The flux decreases, deflecting torque decreases. Then there is an error in measuring instruments. That is a link between this temperature. At the same time, the frictional error also. So, this all arrangement placed on a spindle, and the spindle is placed on a pivot. The pivot initially is okay. After some aging, the roughness maybe takes place. There is a frictional error between the bearings and pivots, and due to this one a slugging operation maybe takes place. Due to this one the deflecting torque decreases. It may cause some error also. And mechanical unbalance, because this all arrangement, the coil which is placed on a spindle, both sides should be balanced condition. Otherwise, one side coil weight is more, other side the coil is less, then the unbalance takes place. This also leads to the overburden on the jewelry bearings and pivots. The frictional error further increases. It leads to common error. And aging error. After continuous usage of these meters, we know that if you are using the moving coil instrument, there is a U-shaped permanent horseshoe magnet. Initially, the horseshoe magnet has a good intensity of magnetic field. After aging continuous some years, this magnetic field may be decrease. This may leads to deflecting torque less. At the same time, due to the aging, the spring tension stress also changes. At the same time, if the temperature changes, the tension or stress in the spring also changes. If spring changes, the controlling torque value changes, which is opposite to the deflecting torque. Thereby, the error may occur while in working. And not only this one, sometimes observational error also. By taking the readings, there is a errors, and that like the parallax errors maybe lead to the wrong observation readings. And also stray field. So because all are the electromagnetic fields, these are the fields are very weak in our instruments. If these instruments are nearby strong magnetic field surrounding area, that magnetic field effect on our instruments, which leads to errors in while reading. And frequency error also while you are using AC, because the coil has a reactance of omega L, that is equal to 2 pi FL. F is a frequency. If input frequency changes, then automatically the reactance value changes corresponding to the flux changes, then deflection torque also changes. So, these are the errors, generally very small, but it is a significant. We have to consider how to overcome these errors, how these errors are occurred in moving coil instrument, moving iron instrument and a dynamometer type instruments, and what are the remedies, general remedies provided in instruments we will learn in this class. Okay. So, what are the general errors? Temperature error, frictional error, mechanical unbalance error, observational errors, aging errors and stray field errors, sometimes frequency errors also present in our electrical instruments. Let us see these errors affect in moving coil instruments, its remedies, and in moving iron instruments its remedies, and dynamometer type wattmeter and its remedies we will see. Now you can see it. Temperature error. What do you mean by the temperature? As you know that the temperature here, what is the temperature? Increase in temperature increase the resistance, because if you know that here the all metals are positive temperature coefficients. Now temperature increases proportionally, the resistance also increased because of positive temperature coefficient for the metals. This temperature may be due to, because this is a coil which is used in our instrument, it has some resistance through which a small current will flows for produce the deflection torque, and this current and this resistance will gives the I square R T by J, that is equal to heat energy. If continuous for the long term, if you are used this instrument and the current is passing through this instrument, it will definitely produce some heat energy. If heat energy produces, resistance value increases. If resistance value increases, then the current which is entered into the coil also decreases. If current decreases, the flux decreases. If flux decreases, the deflecting torque decreases. Once deflection torque decreases, the pointer may not show the correct actual value, that may show below that value. This leads to error in while calculating the readings with our instruments. Okay. So, simple relation, because the electrical students, you know the relation between the, what is the relation between the temperature and the resistance. Okay. Now, here increase in temperature, increase in resistance, the current proportionately decreases, the results low deflection of the coil. So, okay. Now, you can see, and current proportionally decreases, resulting low deflection of coil. Also effects on springs coil. The spring coil's tension decreases. If temp expand more, then looseness takes place. The tension decreases, result in the controlling torque also decreases. Here the deflecting torque changes and controlling torque also changes, thereby it may be leads to some error. Then what are the remedies we are going to take it? So, we cannot avoid, because the coil should be provided inside there is a U-shaped magnet. So, as you know that, so here is a U-shaped magnet, this is a permanent magnet. So, nothing will happen here, north pole, south pole, but we are going to provide the one rectangular coil here on which we are going to provide the winding. So, winding that should be required some minimum resistance. This resistance will changes with temperature changes. So, how to overcome this change in deflecting torque and change in controlling torque. If resistance changes, deflecting torque changes, as the spring heated takes place, then controlling torque also changes. Okay, so thereby, so what is the steps you are going to avoid this one? Let us see what are the remedies. Now, first remedy, by adding a swamping resistance of manganese in series as a multiplier, this effect minimized in case of voltmeter, as you know in previous classes. So once the voltmeter we circuit, we are going to measure here. So we connected the one voltmeter and some shunt, here is the connected the multiplier. Then we are going to use the load, and here we are using the one swapping resistance. The swapping resistance is it has the alpha should be the constant, it does not change its resistance with the change in the temperature. Such a material is the manganese, that is the irrespective of the temperature. Very low temperature coefficient of the material. So it is used as a swamping resistance. Then even change in temperature, the value of in series resistance, that is known as the we can multiplier. Series does not change, so thereby it does not affect on the readings. Okay, this already you know in last class. Now, at the same time, in case of the voltmeter, we are using the sampling resistance made with of the manganese in series with the multiplier. Okay, so in series with the multiplier, we are already seen voltage. So we connect the. So what is the multiplier? So here I want this voltmeter. It is designed for the only 1 volts, but I want to measure the 100 volts. That purpose I connected the some extra resistance. This is known as a multiplier. In series, I am going to connect the one resistance. This is a swamping resistance. So it is made of the manganese material. Okay. So here we connected the one swamping resistance series with the multiplier to avoid the temperature error in voltmeters. For what about the ammeters? So ammeter also, so we are going to extend the ammeter range. We are going to connect the one shunt resistance value, low values. Here the meter resistance value, for example, in case of the ammeter, what is the resistance? For example, here we take the 0.02 ohms. But what is this value? That should be less than 0.02 resistance, because heavy current, that means by diverted in this direction. This resistance are always less than this resistance. Whereas in case of the voltmeter, for example, this voltmeter resistance is the 50 ohms. Then here this should be, you are going to connect nearly 500 ohms. That should be more. So this already you know this, previous class we have seen. Now in this case we are connected the swamping resistance in series with this one, and in case of ammeters we are going to connect, so adding the external shunts and maintaining at the same temperature of the coil in the ammeter by connecting the shunt material made up of the manganese materials. So we are constant material, we are going to maintain the temperature change constantly, so that may not affect our meter readings. Okay, so in ammeters we are going to connect the shunt, and voltmeter we are going to the multiplier or series resistance with the sampling resistance. So these are the two methods generally applied in our instruments. Okay, so one is the sampling resistance made of the manganese connected in series with the voltmeters, and in case of the shunt ammeters we connected the made of the manganese. These are the two methods generally employed in our instruments. Now coming to the another error. So same thing, by using the shunts of manganese across the shunts. Now another error is the frictional error. What do you mean by the frictional error? Let us see. So deflecting torque affected by the friction at the pivot. As we know that, what is the pivot here? So you know that here this is an aluminum frame, this is a spindle, and the spindle is placed on jewelry bearings, both sides. Okay. Now on which I am going to provide it winding, copper winding, on which here copper winding. Okay, this is connected the spring through this one, and it is connected to the another spring, this one. This is the input, this is the output. The spring here is connected as a controlling torque, and another spring is opposite direction is another controlling torque. Now what is happened here? The spindle is placed in pivot. So you can see here the pivot which is placed here are your bearings, you have placed the jewelry bearings. In between there is a frictional error takes place. The deflecting torque affected by the friction at the pivots, by the dust covers on the moving parts. There is a heavy weight also provided by the dust enclosures provided on the instrument, that is effect on the weight on a spindle. By the heavy moving arrangements also affect the frictional error. Friction means it's a easy to move, rotate. Okay. So here how you are going to this one. The deflecting torque affected by the friction at the pivots and by the dust covers on the moving parts, also weight on the spindle, and the heavy moving arrangement. If the coil, the number of turns increases, radius of the area of the radius cross section of the winding increases, weight also increases. Thus pointer also placed on the spindle, and the controlling torque springs also provided on the spindle, and air friction damping, some weights for the gravity control also provided on this one. So total weight on the spindle on a pivots. The pivots are placed in the jewelry bearings. So the bearings and pivots, in between there is a frictional error takes place. This frictional error, due to it may be reduces the deflecting torque, that leads to error. What to do? So we require the frictionless bearings is required. Those errors are the jeweled bearings. Okay. So by using the light construction of the moving system, first of all, so we are going to use the materials very light in weight. So due to the weight on the spindle decreases. Okay, that is the one remedy, and by using the jewel bearings at both sides, so we are going to reduce the friction. So you can see here in the figure also. So what is the here you can see observe here, and here you can observe here. We provided the spindle on a bearings. So here instead of using the ball bearings and roller bearings, we are using the jeweled bearings. Jeweled bearings we are using. Okay. So what are the effects? You can see it. Remedies. By using light construction of the moving system and by using the jewelry bearings, we are going to reduce the frictional loss. At the same time, so there is a possible to fall on the dust in between the pivot and bearings. So there is maybe friction. So that is why we are going to keep this instrument in a dust proof instrument. Keeping moving system in a dust proof case, it can reduce the frictional losses. These are the 3 remedies to reduce the friction losses by using light weight in construction of the moving system and by using jewel bearings and keeping moving system dust free case. Okay. So that is the another one. Now another is the mechanical imbalance. Now we are going to the another error, common error is a now all the air friction damping gravity control or spring control, pointer and coil, all are placed on a spindle. The spindle should be balanced, otherwise one side it may be tilt. The friction on the bearings and pivot also changes, which leads to mechanical vibrations. Dear students, you can observe what will happen if it mechanical unbalance. In our cases, if you are observing in our cases, okay, let us see that one. Now, in mechanical imbalance, that means suppose you see the fan in your house. If one blade, if you remove it, remaining two blades, so it will give the air. Yes, it will give the air, but it may be mechanical vibrations, unbalance takes place while it is rotating. Or if you are the twisting or moving downwards one wing, then automatically here also there is a vibration takes place, sound will gives from the ceiling fan. That is the unbalance in mechanical. Three blades should be at 120 degrees apart at the same level. Otherwise, so there is a mechanical vibrations on the fan, rod and bearings. It may be very quickly, it may be gives the damage to your fan. Okay, that is a example of the mechanical imbalance. So, what is the mechanical imbalance? So, sluggish movement of the moving coil affect the torque produces. So, what is sluggish? Sluggish means, so it is not free movement. It is not free movement. Sluggish, jerks. The jerks may be create the deflection torque. So, first one is the here the sluggish movement of the coil affects the torque produced in, and at the same time, so due to the heat produced also affect the mechanical changes. So, here due to the heat, the balance of the moving system is disturbed, because due to the heat the metals which are provided in this one, there is a linear expansions. Linear expansion of the metals will also unbalance the spindle. It creates the unbalanced weight on a pivot as well as the bearings. Okay, so what are the remedies we have to take? So here the instrument should not be given jerks during the operation. So why you are doing this one with the experiment, don't give the jerk operations. That is the one thing. Instrument should not be given a jerk during the operation. At the same time, it should be kept away from the heater or such appliances surrounding where temperature is more and more, because if the temperature surrounding area increases, the parts inside, metal parts inside our instrument, there is a linear expansion takes place, and due to this one unbalance takes place. Okay, so that's why while you are using the MC coil, you should be keep in mind that, so while using this one, don't give the jerks on the instrument. At the same time, you have to away from the heating surrounding area where you are going to measure it. Okay, so these are the two remedies we have to follow. Now, next, at the same time, these are the few errors in a instrument, and as you know that observational error. So, you are going to, while seeing the readings, because scale is uniform, nothing problem, but what to do, there is a parallax error maybe takes place, parallax error. So, at that time you are going to take the reading exactly 90 degrees, or you can use a mirror in between the split. So, by seeing the image on the mirror, you are going to take the exact reading where it is the pointer is showing. So, that can be used by this observational errors. The aging errors also, so you have to replace the frequently the springs, at the same time some if magnetic field is weakened, so you have to replace the spring as well as the U-shaped magnet after long duration, then you have to recalibrate once again, then you can use it. So these are the few errors takes place in a moving coil instruments. What are the instruments? What are this one? One is the temperature error, frictional errors, mechanical imbalance errors, observational errors and aging errors, and sometimes we can say the stray field errors also we can observe in moving coil instruments, and these errors can be avoided by using the jewelry bearings and placing the spindle on a vertical, and it is placed in the dust free case, and at the same time we can using the manganese material. So there is some extra resistance which has not affected the temperature, that is connected in series in case of the voltmeter and in case parallel in case of the ammeters. So these are the few points you have to remember. Now after coming this, let us see another instrument, moving iron instrument. Similar errors there is. So one extra error in addition to this one. So what is that error? So frequency error maybe takes place in at that case. Okay. So let us see. Now causes of errors in moving iron instruments. What are the cause? The errors are more in AC operation because there is a presence of frequency, and the mechanical failures of the moving parts also. If the moving parts are unable to perform perfectly, or it is not, if it is a sluggish, if it is unbalanced, then it leads to the errors in our instruments. At the same time, due to the external stray magnetic fields surrounding strong magnetic fields leads to the impact on our coils, the inside instrument magnetic field impact, thereby the deflecting torque also changes. Then, so what to do? So let us see. Due to the external stray fields outside magnetic fields. So you have to avoid that one. That purpose we are going to use some remedial measures. What are the measures we will see? Okay. Now the moving iron instruments errors divided as, so commonly divided as, so due to the AC and due to the DC. So due to the DC current, if you apply it as an input, what are the some errors? If used as a AC, then what are the errors? The current or voltage purpose, or whether it's a voltmeter or ammeter. Due to the stray magnetic field, outside magnetic field, the magnetic field of the coil changes and causes errors in the readings with effect of external magnetic fields, because here that instrument, we know that moving iron instrument. What is a moving iron instrument? We have seen the two types. So what that one? So moving iron instrument. So here one is the, so it produces the magnetic field. There is a spindle through which there is a oval shape iron piece, and there is a strong magnetic field inside this one. So this is the magnetic field, and this magnetic field impact on the iron piece, the iron oval shape iron piece try to move this direction, the spindle will move, okay, the spindle will move, then pointer will move this direction. That means here whatever the supply is given here, this is a coil and it produces the magnetic field, that field try to attract the oval shape inside this coil. Due to this one, it is attached to the spindle is placed same arrangements, then it will rotate on a calibrated scale. Okay. So here what will happen? This magnetic field and this magnetic field affect with the stray fields. If you are keeping the outside one magnets, north pole south, this field also affect on this iron piece. Hence the deflecting torque will show a wrong reading of true values. Okay. So that's why the north pole south pole, this outside magnetic field can be shielded while using these instruments. How to that one you can see. So here due to the rise in temperature, what are the common errors? So how the temperature rises? Because it has also winding. So winding has resistance has current flows, then I square or power loss as T by J, Joule constant. We are going to heat is developed. Due to rise in temperature, we know that the spring stiffness increases and the permeability of the core also decreases. So what is the permeability? Because we know that in school level all magnetic property will destroy due to the heating effect. If you want the magnet, you demagnetize the magnet, then so you are going to heat the magnet, then automatically it loses its permeability. It is the capacity to sustain magnetic field is losses. So due to the temperature here, so electromagnets, so what will happen? The permeability of the material decreases, then more current is required to produce the same magnetic flux. Otherwise, due to the heavy current, same I square RT by J heat will develops. So that is the cascading effects takes place here. Okay, so we can see that one. So due to the rise in temperature, what has happened? The spring stiffness increases, and because they become the brittle, and the permeability of the core decreases. Then thereby the hysteresis losses may be occurred and error may be takes place. Okay. At the same time, in AC operation, the meter reading is higher than the normal value. So in case of the AC operation, the frequency effect, AC operation, the meter reading is higher than normal while you are using the DC due to the hysteresis effect, because hysteresis loss is equal to the product of frequency. Okay. So then you can see it if you cross section of the moving iron instrument. Let us see what are these errors. So temperature error already we know. Then let us see the another errors. So as usual, the frictional error, another one. Okay. Now frictional errors, due to the dust collection at the moving parts, there is a friction maybe takes place. If dust in between the our pivot, so you can see here, if it's placed, okay, it is a, if you placed here, what is happen? So there is a pivot and there is a jewelry bearings. In between, if dust is formed, the frictional error increases. It decreases the deflection torque strength. And improper compensation or mechanism also leads to the frictional error. Improper compensation, while calibrating the instrument, you have to improper of this thing maybe increase the frictional errors, and unbalanced mechanical also increase the frictional errors. Next, second error is the observational errors, as you know, similar to the previous one. So due to the zero error, so if you are going to measure, for example, so this instrument is started at 0, 1, 2, 3, so 1, 2, 3 values, and the value, the pointer should be this value, so initially, but due to some problem it is here. So this angle is extra. While doing the 2 amperes, it will shows the only less than 2 amperes. And so while starting the instrument, you have to keep it at 0 position. At the same time, while observation, if you are seeing this side and this side will give the error, you have to give the vertically 90 degrees, then you are going to get the, so no parallax errors. Okay. So that is a one example. Next one is the observational error due to zero errors, another is the parallax error. Generally parallax error, so similar to that one, we can avoid with the help of the mirror placed in between the calibrated scale. Next error is the aging, due to the aging. So due to continuous operation of this moving iron instrument, so the spring maybe, tension maybe, the stress maybe changes, and at the same time the exposure to the high temperature also, the tension in the spring also changes, and it leads to a wrong reading while doing the experiments. At the same time, another error also, here hysteresis errors due to the frequency, and the another error is the eddy currents. Affects in more in AC operation, because eddy current is the square of directly proportional to the WH. So you know that WH is the hysteresis frequency directly proportional to some constant into something into F. Whereas the eddy current loss WE is directly proportional to the B square and F square, some constant to F square. Here the eddy current is directly proportional to the square of the frequency, and both frequencies dominate the hysteresis losses and eddy current losses. Not losses, and the effects also on the system. So due to the eddy current, the system will heat takes place. This hysteresis losses, what will happen? So more current will draw it to produce a same magnetic field, which leads to the deflecting torque changes. The eddy current effect is more in AC operation. Okay, so that is the one. Another error takes place in this one. Now, what are the remedial measures to avoid these errors in instruments? Common errors. What are the common errors? One, temperature error, frictional errors, observational errors, aging errors, and eddy current errors. We have seen what the effect on deflecting torque and controlling torque overall our readings. Now, what are the remedies we have to take? Reduce these all errors. Let us see. Now, remedial first, that is the temperature error. The temperature error can be reduced by using the swamping resistance connected in series in case of the voltmeter and parallel in case of the ammeters, as we discussed in previously. Okay, that is a swamping resistance which is made of the manganese material or constant material, which cannot change its resistance with a change in the temperature, as you know, studied in materials in first year level. Okay, now another error is a observational error. So what is the observational error? So initial correction for zero error placing mirror below the scale. So here we are going to provide the one mirror bit below the calibrated scale. We are going to avoid these errors while taking the observation. And another error is the hysteresis error. So reduced by using a movemental or permeability core, which is having high permeability materials. Okay, so hysteresis can be reduced by silicon content. Already we have seen. Similarly, here we are going to use in our instruments. So with metals, the movemetal or we can use the permeability core is generally used to reduce the hysteresis errors in our moving iron instruments, where it is subjected while using the AC calculations frequency. Now another error is a frequency error. So here is the AC frequency error. How we are going to reduce the frequency? Connecting the capacitor across the moving coil. One capacitor is connected across the moving coil. So coil instruments, moving iron instruments, we are going to, so because we are using the moving iron instruments, we are going to connect the one capacitor effect. So that will, whatever the changes frequencies, so it will avoids. Okay, so correspondingly frequency changes, we know that what is the effect. So here is some omega L is equal to 2 phi FL, omega C that is equal 1 by 2 phi FC. Now here the frequency changes, W value changes, correspondingly frequency changes, correspondingly WC changes. If you connected the, here is a capacitor, correspondingly this is an inductor, then if it changes one direction, it changes other direction. So thereby nullify each other, error is minimized. Okay, so because both are dependent upon the frequency, it is that is the inductive reactance, the directly proportional to the frequency, whereas the capacitive reactance, the inversely proportional to the frequency. So by connecting the one capacitor across this coil which has the inductance value while using the AC, then we are going to nullify this frequency error. Okay. Now coming to the another type of the error is a stray field error. What is the stray field? This is outside field, not in our. For example, in moving iron, we are used the what are the this one. So we use the one coil, okay, and we use the one spindle here, nearby here spindle. The spindle here and we used the one oval shaped iron piece. So, when supply is given to this one, it is magnetized, magnetic field developed. This field linked with this iron piece, it is a magnetized. Now, it acts as a one magnet, it acts as another magnet. So, interaction of these two magnets, there is a deflecting torque is produced. That deflecting torque will move the pointer. In addition to this, if you are placing nearby another one strong magnetic field here, or north pole, south pole, or here, then what will happen? This magnetic field effect on this one, or similarly on this one, or due to the effect, then what will happen? So, deflecting torque without this magnetic field is not equal to the with effect of this external magnetic field. So, we have to avoid it. How we are going to avoid this one? Placing a steel lining as a case or shielding. So, we are going to avoid this effect on our magnetic field by placing a steel lining as the case, because this should be placed in a common case, common box. This box is coated with a steel coating that can avoid the entering of extra outside magnetic field on our instruments. Okay. So, this is one examples. Now, what are the another one? So, another one is a frictional error. Here also there is a spindle, there is a pivot, there is a jewelry bearings. So, by using the similar to the jewelry bearings, we are going to reduce the frictional errors. Okay. And another one is the aging. So, aging means the continuous usage of this machine, this instrument, the inside the parts maybe age takes place. So, replacing the old ones by spare parts and calibrate once again. Okay. So, replacing the old ones by new spares and calibrate once again. Okay. So, these are the some errors takes place in a moving iron instruments. What are the errors? Mainly the temperature errors, stay field errors, frequency errors. Okay. So, similar to the and frictional errors and aging errors. So, these all errors can be avoided with the help of the some simple steps we have seen. Okay. Now, coming to the what do you mean with the accuracy and the standard of methods in measuring instruments? Standard meters and accuracy. So, what is the definition? Let us see. Accuracy means the reading which is given. It is the closeness with which an instrument reading approaches the true value of the quantity being measured. The value which is to be going to measure, that should be nearer to the actual value. That means error difference between the actual value and the measured value should be the very less. That is required. The error may be in some instruments we are going to having the different percentage. For example, in moving coil instruments, this error can be the 2% we are allowed. 2% means the 2 by 100. 0.02% we are going to allow. And moving iron instruments, this error may be 0.75 to 2% we are going to allow. So, because due to this all errors, these errors are maybe if you are taking any measurements, the temperature we cannot avoid change in temperature, and stay magnetic fields, frequency changes. So, due to these errors, we are going to not getting the exact value, a true value. There is a difference. That means the actual value minus the measured value. There is a difference. That may be errors. These errors are may be allowed in case of the moving coil instruments 2% and moving iron instruments from 7.75 to 2% we can allow. What is the definition here? The accuracy means that it is the closeness with which an instrument reading approaches the true value of the quantity being measured. Okay. So, this is accuracy. Actually, what is happening? So, here suppose for example, I take in the one instrument which is a ammeter, and so here my load is suppose for example connected to the one load, and this is one and this load, so there is a printed current here, that is a 1 ampere, but I am using this supply is given to this one, and ammeter is showing that it is only 0.99 amperes only, but it is a standard printed on a 1 ampere, maximum current drawn by this is a 1 ampere, but it's showing the 0.99 amperes. It is almost plus or minus almost is acceptable. Okay, so because it cannot show the exactly true, this 1 ampere is a true value, the 0.99 is a measured value, the difference between this and this value will give the error. So that error is a correction is required. Okay, so the accuracy nearly is allowed. Okay, it is a nearly closeness to the true value, that is a definition. Okay, which an instrument reading approaches the true value. So true, what is the true value? 1 ampere. What is the measured value? 0.99. Okay, so that is the true value. Now what do you mean the standard? Standard means a standard is a physical representation of a unit measurement. Just is a definition. Standard instruments, generally we can see it. Okay, so the standard means the standard is a physical representation of a unit measure. Each is a unit measurement represented by the standard value. Okay, now let us see the accuracy of moving iron instruments or moving coil instruments usually. So what is the order? Already we have seen. Now you can see here the accuracy of moving coil instruments usually is of the order of 2% of full scale deflection. There's the meter is showing the full scale deflection. There is a maybe accuracy may be only 2%. The accuracy of moving coil instruments usually is of order of 2% of full scale deflection, and that means torque by weight ratio is a very high. What is the meaning of torque by weight ratio? This is the torque, the deflecting torque. Deflecting torque is produced by weight. Weight is the coil weight, spindle weight, air friction weighting, and spring weights, all weight. If the weight increases, automatically TD decreases. If TD decreases, deflecting torque decreases, the moment of the deflection decreases. So instead of showing the original this value, it is showing the only, for example, this 9 value, it is showing the only 8.8999 it's showing. So this is a error. That means due to the torque by weight ratio, weight increases, deflecting torque decreases. So as far as possible, the weight of the instrument should be decreases. Then weight for weight ratio minimum, then it will show us a good reading. Okay. Now next another aspect is the, so what reason is the that much, and another the accuracy of moving iron instruments vary between the 0.75% to the 2% depending on the frequency value. If the frequency value changes, so this also changes, and that's why it is the limit between this value. So whereas in the moving coil instrument only the frequency, independent of the frequency, it is the 2%. Okay. Now what are the accuracy, the moving coil? So moving iron instruments accuracy depend upon the watt factors. Watt factors means we have seen accuracy of the moving iron instruments is the 0.75% to 2%. So whereas the accuracy in moving coil instruments is 2%, that changes 2%. The value will changes 2%. Why? Because torque by weight ratio is a very high in case of the moving coil instruments, because it is placed in the aluminum frame. Aluminum frame has a weight on which there is a coil winding, copper winding is wound. There is a place and springs, some counterweights, and this all things will weight on the instrument. But in case of the moving iron instruments, it is a range from 0.75 to 2% depending on the frequency. At the same time, what are the main factors affect this accuracy? So accuracy of a moving iron instrument is affected by the following factors. What are the factors? Let us see. So one is the temperature. The temperature increase the resistance of the solenoid, decrease the torque, as we discussed in first case also. Okay, temperature increases, and what will happen? Resistance of the coil also increases, then current flowing through the coil decreases, then the deflecting torque also, the current decreases, what will flux also decreases, and the flux decreases, deflecting torque also decreases. So this effect maybe takes place, decrease in torque. Okay, as you know this one. Next, not only the temperature, aging also one factor for errors in moving coil instruments. So what is that one? As time passes, the springs becomes more stiff, the brittleness increases, stiffness increases. The controlling torque so produced also, if stiffness increases, the controlling torque also increases, thereby deflecting torque opposed by more controlling torque, then the reading may be wrong reading. Hence what to do? So we have to replace the frequently the springs. That's why we are using the phosphorus branch hair springs, the materials. After long period we have to change it. Okay. Now another is here we use the iron piece. So iron. So permeability also changes. So already we have seen. So what to do that one? Another one is the permeability of the core material. So change in permeability affects the torque. So what is the permeability? It is the ability to retain a magnetic field. So that if the temperature changes, the permeability changes. If the permeability changes, the field flux developed also changes. The flux changes, deflecting torque also changes. So keep in mind. Next, another is frictional errors. Increase of friction in the moving system affects the moving parts. So if the moving parts are more, automatically the friction on the pivot and bearings increases. And another effect is the stay field. So you can see stay field. Stay field means, so outside magnetic field impact on inside magnetic flux, then automatically it will show the wrong readings. Okay, and now coming to the another instrument. So we have seen in this one the accuracy depend upon the permeability of the core, friction of the core, friction on a spindle, and stray fields, and frequency, and so different things affect on moving iron instruments we have seen. Now the last one is the another important is the dynamometer type wattmeters or dynamometer type instruments. What are the common errors? Everywhere common errors is these errors only, same frequency error, same eddy current errors, same hysteresis errors, same stay magnetic field errors, and the weight, the torque by weight ratio, these are the dominating. Let us see. Okay, so you can see it. So you can see this is a one physical construction. So two coils placed side by side, in between there is another coil, moving coil is placed. All arrangement you can see it placed on the spindle, and the spindle is placed on the well bearings. Okay, so what are the errors may be occurred? Common errors. Low torque by weight ratio, because here the weight is more, you can see it. Two coils having the high thickness series coils, because series current has to flow through this one, that's why the weight of the coils increases, diameter of the coil increased, less number of turns but more weight. At the same time the coil, the moving coil also placed, here you can see moving coil because the thin wire and its number of turns is more to produce a flux. So the weight on the pivoted also increases, that's why the low torque by weight ratio of dynamometer instruments, it affects on errors. And another is a frequency error, because it is operated AC and DC. While operating the AC, so automatically this is a coil, this coil having the inductance, then omega L F is equal to 5 F. Okay, so L frequency error. If this changes, automatically this value also, the ohmic value also changes, then current changes and flux changes, deflecting torque changes, thereby total reading may be error. And another is the eddy current errors, because here we placed air cord, even then eddy currents may be produced. This may leads to heating of the place. And another error is the stray magnetic field errors, similar to the previous case. Temperature increases, the stiffness of the spring increased and resistance decreases. Everything error may be takes place, similar to the previous case. Now let us see how to this minimized here. So what do you mean by the low weight by weight ratio? Now let us see this one first. So what do you mean by the low torque per weight ratio depend upon what factors? So here we can see it. Low torque per weight ratio error depends on mainly the magnetic field produced by the instrument is very weak, because the coils used in the instruments are air cooled. As you know that this is a coil air cooled. If placed some iron piece core material on which there is known as a solenoid, toroid, this is a solenoid. Same 1 ampere current producing the flux of here for example 2 milliwebers. But here same 1 ampere, so it producing the 2.5 milliwebers. That means here is the iron core is used, is a magnetic material. Now here is the air as a dielectric media. So here we used the previous figure, we used the here is the air cord, one coil, fixed coil, another turns, here the air cord, both are used. So to produce a strong magnetic field, we require the more current. Indirectly, more current takes place. Okay, the magnetic field produced by the instrument is very weak because because air cord, because the coils used in the instruments are air cord. That is a one reason for the low weight. Sorry, the torque by weight ratio is less. A large number of turns are required to produce a required torque, because here due to this one, so what will happen? So require the more current. Here we know that flux is equal to N into I. N is the number of turns. Current here previously we required the current 1 ampere current is required, but flux is less. So what will happen? So if I increase the current, then so our current bill increases. That's why instead of same 1 ampere current, I want the 2.5 milliwebers. Then instead of this one, same 1 ampere, instead of using the 1.1 ampere, now I am going to increase the one more turn. If turn increases, the weight of the copper increases and resistance of the winding also increases. This leads to mechanical unbalance and weight. Torque by weight ratio increases. Okay, next is a large number of turns makes a heavy moving system, as already we discussed, and due to this torque by weight ratio is very low. That means whatever the torque is produced is very low due to the weight increased due to these reasons. Number of turns increases because it is placed in the air core. So we require the some magnetic field. To produce the same magnetic field, we are going to add the more number of turns, weight increases. Okay, this is the reason for one error in a dynamometer type instrument. Okay, so the torque per weight ratio is very low. Why? These are the reasons. Now coming to the these instruments used for the DC as well as the AC. This instrument can be converted to the ammeter, when converted to the voltmeter, we convert to the wattmeter. Now while you are using the AC system, then there is automatically there is a frequency effect on this one. So what is the frequency error? Let us see. The frequency error occur due to what is the reason? Main changing impedance of the operating coils. As we know that, so frequency error omega L, the impedance is equal Z. Z is equal R plus J of XL. Here, so what is the XL? XL is equal here omega L. Omega is equal to 5 FL. F is the frequency. Okay, if the frequency changes, omega L changes. Omega L changes, impedance changes. That's the ohmic value. The ohmic value changes. Sometimes increases, sometimes decreases corresponding to the change in frequency. That leads to error in the instrument. Okay, now change in the magnitude of eddy currents set up in the metal parts of instrument near to the operating portion also impact. That means here frequency, the frequency changes. As we know that, what is the frequency? Eddy current loss. We know that eddy current loss is directly equal to the square of the frequency. So if the eddy current increases, then heat will takes place in the system. That effect. If the heat takes place, everything goes wrong. Change in magnitude of eddy currents set up in the metal parts of instrument near to the operating system, there is a possibility increase in temperature. Okay, now eddy currents are induced in the metal parts of the instruments because that's why in our other instruments, in motors, DC motors as you know, AC motors as you know, the core is laminated. The core is laminated instead of solid one. What we have seen? So instead of solid piece, so we are going to use it. This is a laminated. Make the pieces. Each piece in between there is a varnish insulation. So thereby eddy current losses decreases. Okay, in case of our DC motors and AC motors, where each lamination is a 0.35 mm to 0.5 mm thickness. And in case of the transformers core, so sometimes we are going to use a amorphous core, that is a very thin, just like is a paper thickness, that is used in amorphous transformers, so to reduce the eddy current losses. Okay, now the induced eddy currents will produce some torque. That the torque also affect on that one. This torque will produce some error. So actually produced by the torque is impacted by this eddy current produced torque. Thereby, so what will mal-operation of our instrument? The eddy currents error is reduced by keeping the metal in the support of the coil and other structural parts to the minimum possible. Okay, so it is what to do here. What are the eddy current depending on the metals? Because what are the metals are used in the instrument? If the metals are used in this one, it is linked with the magnetic field. If magnetic field link is, then it induces a currents as per Faraday's laws of electromagnetic induction. If these are the solid one, there automatically there is a current flows in the metal parts and it produces its own current, and that current is known as the eddy currents. Due to this eddy currents, it produces its own magnetic field. This field always opposes the main field as per our Lenz's law. So thereby what will happen? The main field decreases. That decrease in main field deflect torque also decreases and meter reading also reduced. Okay, so that's why, so as possible as use minimum metallic parts in a dynamometer wattmeter to reduce the eddy current losses. This is the meaning. Okay, so less you use the less number of metal parts in instruments. If you want to use it, make it laminations to reduce the eddy current effects. Okay, now coming to the another impact is the stray magnetic field errors. So as you know that, so here you are observed, this is a fixed coil, this is a fixed coil in series, and here is a moving coil in center, and it produces its own magnetic field it produces its own magnetic field. This magnetic field is a rotor magnetic field, this stator magnetic field for example. Fixed magnetic field, this is a spindle magnetic field. These two magnetic field interaction, there is a torque is developed. The torque is directly proportional to the TD, directly proportional to this phi 1 and phi 2. If in its ear deflection torque, if another magnet is placed nearby ear instrument, north and south pole, this effect on the torque, it is a phi 3, then automatically this value changes. To avoid that, so similarly we are going to use a steel screening, steel lining in the instrument. Okay, previously we have used the MA instrument. So the operating field in the instrument is weak because the coil air core, because of the air core coil. The operating field is very much affected by the external magnetic field, because strong magnetic field affect the weak magnetic field which is inside the instrument. The instrument is protected from external magnetic field by metal shields, just like steel lining. Okay, that is the stray magnetic field errors. Now coming to the as usual error, the temperature error. So what is the temperature? Similar to the previous case also same. High current carried by the coils will raise the temperature, and temperature raise will change the resistance of the coil because directly proportional to the alpha changes. Change in impedance will produce some error. So current changes, automatically ohmic value changes. The temperature error is neutralized by temperature compensating resistor, that is made of the constant material. Those materials does not change its resistance with change in temperature. That is the alpha should be constant. That is the manganese materials or constant materials are used as a resistive materials in the instruments to avoid these errors. Okay, now these are the some errors we have seen in our instruments. Okay, so this is the temperature errors. What are the errors in a dynamometer type wattmeters? That is mainly torque for weight ratio error and frictional losses error and frequency errors, eddy current errors and stray field errors and temperature errors in dynamometer type errors. Okay, these are the errors in our instruments. Now let us summarize what we have seen in this class. Okay, so what is the time? 1. Okay, no problem. Now let us summarize this thing. So in this class we learned, okay, so in this class we have learned that the errors in moving coil instruments. In moving coil instruments, at a glance I am going to summarize it. So errors in moving coil instruments, errors in moving iron instruments, errors in moving dynamometer instruments. In errors in moving coil instruments are mainly the temperature error. Change in temperature directly proportional to the change in the coil temperature and spring temperatures. Thereby deflecting torque and controlling torque changes. So that can be avoided by connecting voltmeter with a manganese material in series, whereas a shunt across the ammeters. And frictional error can be reduced by the light in weight construction on a spindle. And aging of these moving coil instruments can be reduced by changing the frequent springs and U-shaped magnet after long period and pre-calibration once again. And mechanical unbalance maybe takes place if you are using the more number of metals moving parts in instruments. So remedy was don't subject to any jerks during your operation. Keep the spindle vertical and keep the instrument away from the heating areas where you are going to measure. We have seen. And observation errors also we have seen that. So due to the parallax errors, and even then, so we are going to errors may be present in a good meters. The errors may be nearly 0.05 percentage to 5 percentage on a full scale deflection we are going to allow in moving coil instruments. Okay. So, here the sensitivity of the instruments depend on the torque by weight ratio. The sensitivity also depend upon the ohms per volts. So, actually I forget it. So, here sensitivity of the instrument depend upon the ohms per volts. For example, there is a 20,000 ohms per volts having the more sensitive comparing to the 10,000 ohms per volts meters. Okay, the sensitivity of the meters. Now, coming to the these instruments, coming to the another moving iron instruments, here also the main errors are the temperature errors and stray field errors, and that is the temperature also it changes. Okay, the temperature increases, the temperature stiffness of the spring also increases, change in the resistance also increases, the torque weight ratio is light and the frictional errors also small, and so we are using the stray field purpose, we are using the different methods, the steel, sheet steel lining to the large scale, we are going to avoid the external effect of that thing. So, here, so we know that the torque is produced is a very less in meters, that is maybe the deflecting torque in meters produces the 0.00005. So, generally, so we are going to use them this effects, the stray field change in input frequency errors can be avoided by connecting the one capacitor in parallel to the coil, we are going to avoid the frequency errors. And coming to the dynamometer type wattmeter errors, so we know that there is a torque per weight ratio very low due to this extra weightages, and frequency errors also we have seen, and eddy current errors and external magnetic field stray errors and temperature errors also we have seen, and the same time we have seen some remedies also. Okay. So, by using the friction of the jewelry bearings and by placing this all equipments in a dust proof covers, and by using the some constant alpha change in temperature with the change in resistance, alpha is constant materials are you going to using, and we are going to approximately maintain the errors less. Okay. So, these are the some errors in our instruments generally used in our laboratories or in workshops or wherever we required. Okay. So, if you have any doubts, we will clear in the next class. Thank you for listening my class.